I wanted to learn how computers work, but I can't see what's happening inside a transistor, so I'm making one out of wood.
Welcome to Zoe Needs a Hobby.
The plan is to build a Turing Complete computer with 288 bits of RAM using a von Neumann architecture. Don't worry if you don't know what that means. We will get there. So far, we have the arithmetic logic unit, which is just a glorified calculator, the input, which is like the keyboard of a computer, and the output, which gets us information from the computer. But I'm not going to make you wait for the action. Let's see what it can do. We input the numbers in binary here. The marbles mean 1, empty space means 0. So 43 would be 32 plus 8 plus 2 plus 1. Just hit the lever to enter the number. This machine can add. Let's add 7. And we can print out our result. Silver marbles mean 1s, white marbles mean 0s. 32 plus 16 plus 2 equals 50. So apparently 43 plus 7 is 50. We can also subtract. We send a marble down here to switch to subtraction mode. Let's subtract 25 from 50. 25 is 16 plus 8 plus 1. And look at that. 50 minus 25 is 16 plus 8 plus 1, or 25. You might be wondering how this all works, and we are gonna get to that. But first, let's take a look at the big picture. Modern computers generally use von Neumann architecture, which is impressive since John von Neumann first described it in 1945. Computers with von Neumann architecture need 5 components: an input device, a way to do math and logic, an output device, like a computer screen, a way to store, access, and change memory, and a CPU, which reads and executes the instructions stored in memory. So it looks like I have 3 of the 5 steps done, but the memory and CPU are way more complicated than anything I've built so far, so we still have a long ways to go. So I said the computer would be Turing Complete. There are many great resources on what that means, but the quick version is that this computer, with enough time and memory, would be able to do anything even the most sophisticated computer would be able to do. The only difference is this computer will do it trillions of times slower, and it would need a warehouse full of memory. So I looked it up, and a top-of-the-line supercomputer has over a petabyte of memory. So to match that, this computer would need 3 million warehouses full of RAM. The first version of this computer should have enough memory to run algorithms like calculating a list of prime numbers or playing an extremely simple game. It would not be hard to continue to add more memory, but right now I'm aiming to build 288 bits of memory, which in this case means it will hold 32 slots of memory, and each of those slots can hold a 9-digit binary number. And any of these slots can be read or changed in any order. That's what RAM means. Let's do a 40-second rundown of binary. In base 10, the digit on the right represents how many 1s we have, and each digit to the left gets multiplied by 10 more than the last. In binary, it is exactly the same. We just multiply each digit by 2 instead of 10. So we have the 1s place, the 2s place, the 2 times 2s or 4s place, and so on. Since our only digits are 1 and 0, a 1 in the 2s place adds 2 to our total number. So 1, 1, 0 would be 4 plus 2 plus 0, or 6. That's it. That's binary. Now, let's look at how addition and subtraction works. This part is called the register, and it holds the number the computer is doing math to at any moment. When these switches point to the left, it means 0, and to the right, it means 1. You can read the number it stores from bottom to top. Addition in binary is just like addition in the base 10 we know. The only difference is instead of carrying our 10s to the next digit, we carry our 2s. So for 0 plus 1, we get 1 and we're done. So we send the marble away through the hole in the middle. For 1 plus 1, we get 2, and we carry our 2 over to the next digit to the left and get 0 in the 1's place. Only here, we put the next digit to the left underneath the first digit because gravity. All these connectors going down just make sure when we put a 1 in the 16th place in the input, we add it to the 16th place in the register. Sending a marble down one of these two channels on the left controls if the marbles carry the 2 or 1 plus 1 for addition, or borrow the 2 for 0 minus 1 for subtraction. Subtracting in binary is exactly the same as adding in binary, except when we do 1 minus 1, we get 0 and are done. And when we try to do 0 minus 1, we need to borrow 2 from the next digit to the right, or down, and then are left with 2 minus 1 is 1, and subtract 1 all over again from the next digit. In binary, addition and subtraction use the exact same steps, just in opposite cases. Now here's where my computer differs from modern computers. Instead of having a circuit that directly subtracts, modern computers multiply a number by -1 and then add it. They do this by using something called a 2's complement. This video is already extremely dense and long, so I'm not going to get into it here. But my computer can also find 2's complements and use them to do math with negative numbers. I really can't tell if this is getting too in the weeds, so if you're interested in a video that explains how computers find 2's complements and see my computer use 2's complements to do math with negative numbers, let me know in the comments. Also, if you have any questions, I would love to answer them in the comments. You probably get how the input works already. Just push this lever to get these bars out of the way and release the marbles. But you may be wondering why the marbles go through all these zigzags. No, it isn't to stretch out the length of this video. One issue with my design is that it's possible for 2 marbles to slip through a flip-flop at the same time. And then the second marble doesn't get counted. My solution was to slow down each digit by a different amount, so they all reach the register at slightly different times, and there are no overlaps. For the output, the register flips a switch that sends the marble to one lever for a 1 and another one for a 0. When you drop a marble down this channel to initiate an output, the levers pull threads that get directed by these pulleys to pull on these discs to release the correct type of marble to the correct column. The output has many of these stacked together, one for each digit. I just made this model to show off the internals. The arithmetic logic unit will need to do more than just add and subtract. If you want, you can pause now and see if you can figure out what these other functions do. The CPU will be able to send a marble here to set the number stored in the register back to 0. If the digit is at 0, the marble just moves past it, but if it is at 1, it sets it to 0. Send a marble here, and it will end up in the right channel if the register is storing 0, and to the left if it is storing anything else. This is how we program conditional logic. If the register is 0, then go to a different part of the code. Send a marble here to store the number in the register to the memory, just like how sending a marble to the output channel sends the number to the output. Just like the input though, The memory stores zeros as an empty spot, and a sneaky one. You can see how a user will input a number to the register, but most of the time in practice, numbers will be coming from the memory. Send a number from the memory here, and it bypasses the input and still goes to the correct digits of the register. And it makes sure the marbles get spaced out over time to prevent errors. I started designing this 12 years ago and building it in earnest last year. The design has gone through hundreds of iterations. At first, I based its design off of a system that reads its instructions off of punch cards and doesn't even store its memory in binary, but as the rotation of gears. It took many small steps to get to the design I am using now. I needed to plan out the big picture design of the whole computer before making any of the parts to make sure that each part would be able to connect to everything it needed to connect to. I would love to continue making this computer and to make more detailed build and design videos. I need your help. As of recording this, I have 22 subscribers, most of whom are my friends. Liking and subscribing would have an enormous impact on making this project sustainable. And if you want to help even more, just $2 a month unlocks all of my Patreon content and gets your name in the credits. Thanks for watching. A way to do math and logic. Sorry, your face.
There's a frog in the water. I'm sorry.
There's a frog in the water.
It's where. See where that stick is?
Take your phone.
You see it?
No, I see the stick.
There's a stick. Go closer to the stick. You'll see it's next to that leaf. See that yellow leaf on the right side of the stick? It's literally right next to the yellow leaf. Other stick, other yellow leaf. It's blended in. Here, hold this. Let me show you. You see it?
Oh my gosh, you have such good eyes. How did you see that?
I saw it swimming, and that's why I was like, oh!
Wow, you're blessed. Okay, well that's pretty good content.